Hello, my name is Method, and today we'll present Factorized Gaussian process variational autoencoder model. This is a joint work with Michael Pierce from University of Warwick and Vincent Fortuyn from ETH Zurich. For start, let's consider the following problem. Given some rotated images of an MNIST digit and a new previously unseen angle, we want to generate a rotation of that digit. Now the question is, can we learn to do this directly from the data? A family of models that has been introduced recently and shown to excel at such tasks combine well-known Gaussian processes and variational autoencoders. How exactly? For that, let's first look at the elbow of a plane VAE. Here, y denotes our high-dimensional dataset and z denotes the latent vectors. If we focus on the KL part of the elbow, we see that a standard Gaussian IID prior is used, which factorizes over the entire dataset. On contrary, in GP-VAEs, GP prior is used. We see that a separate GP prior is placed over the entire dataset in each of the L latent channels. Additionally, we make use of the so-called auxiliary data denoted by X. And what is auxiliary data? It is the metadata that is leveraged to improve latent representations. For example, in the rotated MNIST, each image is associated with a digit ID and an angle. Another example is price dataset, where each image is connected with a character style and a character pose. With GP priors, we incorporate such information in our models so that images with similar auxiliary data have similar latent representations. So in essence, in GP-VAEs, we are endowing VAEs with desirable Bayesian properties of GPs. This has been shown to lead to favorable performance on various tasks, from conditional generation to time series imputation. However, GPs give rise to the cubic inference, which is not acceptable in the big data regime in which VAEs perform best. Moreover, since as we saw earlier, GP prior is placed over the entire dataset, these models are no longer amenable to mini-batching. This necessitates the development of non-trivial approximations, which has been the focus of some of the recent literature in the field. In this work, we instead used two very simple, yet still underexplored ideas to scale such models. First idea is that instead of placing one large GP over an entire dataset in each of the latent channels, we propose to split this up into multiple local GPs. On the rotated MNIST, that boils down to placing a GP over all the rotated images of a single digit. Second idea is to utilize different GP priors in different subsets of latent channels. This gives rise to what we refer to in our work as local and global variables. Local variables are meant to capture correlations among rotated images of the same digit and are unique to each image. On the other side, with global variables, we are after angle-agnostic properties of each image, hence these variables are shared among all rotations of a given digit. Both ideas together give rise to the elbow that is both amenable to mini-batching and has much reduced GP complexity. We provide technical details in the paper. While we have focused on the rotated MNIST example in our work and our presentation here, we would like to point out that factorization idea is more general and can be applied every time our auxiliary data space has a product structure, meaning it consists of several independent feature sets. Moreover, it can be nicely combined with some of the aforementioned work on scaling GP-VAEs in cases where inference in local GPs is still intractable. In the experiment on the rotated MNIST dataset, we compare our proposed factorized model with a GP-VAE model in Casale et al. In their work, GP-VAE models were first introduced, and a low-rank approximation of the kernel matrix is used alongside Taylor approximation of the elbow in order to get around computational challenges. We show that our approach is more scalable both in theory and practice while achieving competitive performance. Both GP-VAE approaches, strongly outperforming conditional VAE approach, speaks to the importance of incorporating GP priors for improved results on this and similar experiments. So the take-home message here is that before resorting to sophisticated approximations in order to scale GP-VAE models, think about factorization. Thank you for your attention.